Okay, you're back. I discovered something uh, Friday, actually, Friday afternoon, late Friday afternoon. My wife's out of town visiting her grandbabies in California. I wish I could be there, but I can't. I've, but if I wasn't there, I'd just soon be doing this with you all. But anyway, um, uh, so here we go. Uh, I forgot what I was going to say. Oh, but I discovered this new thing that if I use Chrome, if I use Chrome, Google Chrome, to do my YouTube videos, they load much faster. They always take. It works beautifully. It's when I'm in Firefox and stuff like that. So I just stay completely out of Blackboard and out of Firefox when I really don't have anything bad to say about Firefox. It's just that YouTube is not a Firefox program or app. It is Google, and so your videos work much better on Google. Anyway, we're going to talk about force. Of course, this was developed by physics people, so we've got to have Yoda in the corner. All right, and I'm going to probably go off a little bit on force here. Force, how much one object pushes or pulls on another object. And there's two kinds of forces. There's forces at a distance and forces, contact forces. And we're pretty much, in sports, we look at, of course, contact forces when forces smack into each other. All right, that's what we do. So, example, here's a basketball sitting on the floor. The earth exerts a gravitational force on the ball, and the floor exerts a support force on the ball coming up. Now, this is very crucial. You've probably always heard for every action there's an opposite and equal reaction. What's going on right here? This is not the opposite and equal reactions. Yeah, scratch your head. They're not. They're not. When we talk about force equal and opposite reactions, I'm going to show you that real quick because this is a very important thing. I know you're going to get in arguments with you're going to go tell your friends or something. Some of you are going to say, "Hey, look, that's not the opposite," and then you're not going to know it that well, and they're going to think, "Ah, you're an idiot. You don't know what you're talking about." But look, here's the deal. Here's the deal. And I just spent, and I guess I'm torturing you with this because I just spent like 15 minutes with my Physics 210 class explaining this, and I did it via video because I kind of what I do is I do little lectures like you get, and then we go into when we're actually in class in the lecture, they work problems and they turn one in for credit. But anyway, makes the class go much better for them, you know. And so, but anyway, here's the deal. Here's the deal. So notes for lesson 5, and this will have nothing. There's nothing on the homework. You can skip this if you want, um, because this doesn't. But it'll come up later in the course. All right. So let's say I've got this table and I've got this book sitting on the table. All right. Well, that represents the center of mass of the book. All right. It's being pulled down, the weight of it, and the weight is equal to its mass times the acceleration due to gravity. We'll deal a lot with this guy. mg, where g is the acceleration due to gravity, 9.8 meters per second squared, going in a negative direction, going down or towards the center of the Earth, actually. Now, a lot of people think the reaction force is the table at the center of mass pushing back up on the book, which we call the normal force because it's the force that's perpendicular to the surface of whatever the object is resting on. But that is not the equal and opposite reaction force, because both of these forces are acting on the book. Equal and opposite reaction means if this would probably be better. You'd probably understand this better if I had two ice skaters, okay, and they're holding onto a rope, all right? So I got these two ice skaters. I've only got one so far. There's the little ice skates, okay, so they're holding onto this rope between them, all right? So she's got a hold of it here. Okay, she's wearing a dress. Sexist pig that I am. Anyway, so they're both pulling on this. She's pulling him this way, the tension in the rope going this way. He's pulling this way, tension in the rope going that way. You understand that. And that T is equal to negative T. You get that. This one's a little more different. This one is, you've got the book sitting on the table. We'll put it on the table there, Doc. All right, there we go. Book sitting on the table. The weight of the book coming down this way. You know what the reaction force is? The book has mass, so therefore we don't know why yet. We don't know how gravity works. We just know it does. And by experiment over and over and over and over and over again, we have found that gravity works. We don't know why two massive objects attract each other. We don't know how it works. We just know it does. We're getting real close to discovering maybe these little things called gravitons that make it all work. Kind of like in the new standard model now of quarks and leptons and the electron and all that kind of stuff that makes up matter in the whole universe. Here it is. The reaction force is the book pulling up on Earth. Here's the Earth sitting here. With the same force. So with the force of the weight of the book, let's say the book weighs 4 pounds. So the book is pulling up the Earth with a force of 4 pounds. Is that going to move the Earth? Maybe in a Carole King song, but not here. All right. All right, I'll go on to track 3 and we'll get through the slides. I just wanted to take a little detour on that.